Hello, this is MAT221. This is Calculus 1. This is Mrs. Johnson. I have been a little bit sick and have had no voice, but I'm going to try my best here to do implicit differentiation with you. See if you can bear with me through this. So when we started looking at functions, we knew that the tangent line to the curve can be drawn to any function. But even when something is not a function, say in this case, when we have a circle that is not a function but a relation, we should still be able to draw a slope of the tangent line to this curve. So we should still be able to find a derivative. If I took the derivative of each piece as I move across this expression, and doing the same thing to both sides of the equation, I would get the derivative of x squared, which is 2x, the derivative of y squared, which when we use the chain rule is the derivative of the outside function, which is the 2, bringing the 2 to the front and then multiplying by y, times the derivative of the inside function, that we talked about a little bit in the last section with the chain rule, times the derivative with respect to x of 1, which is equal to 0. If you notice, when we use the chain rule here, we don't have a rule yet for the derivative of the inside function here, y, so we just call it the derivative of y with respect to x. When I now try to isolate dy dx and get it by itself, I would subtract 2x from both sides, then divide by 2y, and then reducing, I get dy dx is equal to negative x over y. This actually makes sense to us when we think of it. If we pick different points on the curve, say if we picked this point right here, which is the point 0, 1 on this unit circle. If I put 0 in for x and 1 in for y, I get the derivative at this point 0, 1 would equal negative 0 over 1, which is equal to 0, which makes sense to us because the tangent line to the curve at this point is equal to 0. Now if I took up another point on the curve, say this point, which is the point 1, 0, x is equal to 1, y is equal to 0, we get an undefined expression, which again makes sense to us because the tangent line to the curve is vertical and therefore does not exist or is undefined. So we could take any point on the curve now at any point on this circle and get the derivative. This type of procedure that we just talked about is called implicit differentiation. It's when we can't solve the equation for just y by itself. In this particular case, you can see that y cannot get solved. This cannot be solved for y just by itself, as opposed to explicit functions, which can get solved. Y equals. These type of expressions cannot. We can still do the same procedure, however, as we move across the curve. We take the derivative of each piece as I move across this expression, but with respect to x. And we're using the chain rule wherever we see a y in the expression. For instance, in this first expression, the derivative of 2y, the 2 is a constant multiple, so I can pull it out to the front. And then I take the derivative of what's left, which is the derivative of y with respect to x, equals the next expression. I have x squared. That we already know. That's a simple, just take the derivative, which is 2x. Plus, here I have another chain rule because I have a y function inside the sine function. So I would take the derivative of the outside piece, which is the derivative of sine is equal to cosine, leaving the inside function untouched, so it would be cosine of y, multiplied by the derivative of the inside function, which would give me a dy dx. So you saw how we now took this using the chain rule. The 2 is the constant multiple. Take the derivative of y, which is dy dx. The derivative of x squared with respect to x, notice the variables match. If the variables match, then we just take a straight derivative, which is 2x. Here we have the derivative of sine. Again, the derivative of the outside piece is cosine, leaving the inside function, multiplied by the derivative of the inside function with respect to x, which is dy dx. Again, let's gather the dy dx's on the same side and solve for dy dx. So I gathered this piece, which has a dy dx in it, to this side of the expression. And then I factor that like GCF out. And again, solving for dy dx, getting it by itself. We get an expression now for the derivative of y with respect to x of this implicit function, this function that cannot be solved for y. Notice most of the time, our expression for dy dx ends up being some type of an expression including both x and y. This doesn't always happen, but it often happens when I take the derivative implicitly. So this technique is called implicit differentiation because the function that we're starting with right here is a function that cannot be solved for y. So therefore it is called an implicit function as opposed to an explicit function where you can get it as a y equals. Here's our procedure. We simply differentiate both sides with respect to x every term along the expression. And then secondly, use our algebra to solve for dy dx, get dy dx by itself using algebra. So let's do another expression here. Let's find the equation of the tangent line and the normal line to the curve of x squared minus xy plus y squared equals 7 at the point of tangency -1, 2. And by the way, if you put -1, 2 into this expression, if we put in -1, you see that the expression for y would equal 2. So we're given the point of tangency and we're given this implicit function. So let's take the derivative piece by piece. So we need the slope of the tangent line to the curve at -1, 2, but first we have to find dy dx, or the first derivative of this expression. Going term by term, I get the derivative of x squared with respect to x, which is 2x, minus, and I put brackets here because I noticed that this is actually the product rule, because it's the function x times the function y. And using the product rule, we have the first function, don't do anything to it, times the derivative of the second, plus the second function times the derivative of the first, which in this case is just 1. Now I put the negative outside so I remembered to eventually distribute that negative throughout the product rule. Then I take the derivative of y squared, which is the 2 comes to the front, leaving the inside function alone, subtracting 1 from the exponent gives us 2y, times the derivative of this inside function y, which is dy dx. I don't know what that is, so I just put dy dx, equals the derivative of 7, which is a constant, which is equal to 0. Again, distributing the negative through those brackets, and now gathering like terms, so the dy dx's are on the same side, but the y gets brought to the other side with an addition, and the 2x gets brought to the other side with a -2x. Factoring out the dy dx, I get the common factors here of 2y minus x, or you could say -x plus 2y. And then dividing both sides by those brackets or those parentheses, I get the derivative of this expression. All right, so now let's continue to try to answer the actual question. The question says, find the equations of the lines that are tangent and normal to this curve at this point of tangency. So the next thing we do is we'd use this derivative we just found, this implicit derivative we just found, and putting in the point that was given to us, the point of tangency, we can then find the slope of the curve at this point. So putting in 2 in for every y and -1 in for every x, we get 4/5. So 4/5 is the slope of the curve of this implicit curve at the point -1, 2. So now let's actually find our tangent line and our normal line. So our tangent line, putting it into the equation of a line, is equal to y equals 4/5, which is the slope of the curve there, at the point of tangency, x minus -1, which becomes +1 minus 2. Remember, the normal line to the curve is the line that is perpendicular to the tangent line to the curve. And I get -5/4 x minus 1, x minus -1, x minus -1, which is +1 minus 2. There's the tangent line and the normal line to the curve. Now remember, we can take as many derivatives as we want to. We talked about taking the first derivative, the second derivative, and so forth. The same thing applies here for implicit differentiation, where we can take the higher order derivatives. So if I asked you to find the second derivative of this implicit curve, we would have to take the derivative of the derivative. So let's try one of these implicitly. Now again, you can see it's implicit differentiation because I couldn't get this in just terms of y because of the square. It'd have a plus or minus square root and so forth. This is an implicit curve. So I take the derivative first term by term. When I do, I take the derivative of 2x to the third. This is an x. I just take a straight derivative because it's taking the derivative with respect to x. So this would be 6x squared. Minus, here I have the chain rule because the inside function is not x, it's a y. So it would be the -3 gets pulled to the front. Then I take the derivative of x squared, which the 2 comes down, so 2 times 3 is -6, leaving the inside function alone, so that's at y, to the first power, so y to the first power, multiplied by the derivative of that inside function. Now I use Newton's notation here, but often we'd like to stay with Leibniz notation because of the fact that y and y prime sometimes look alike. This looks almost like a y to the first, but it is not. And the derivative of 7 is equal to 0. I now gather my terms to solve for y prime. Simplifying, I get y prime is equal to x squared over y. This is the first derivative of this function. We're asked to find the second derivative, so we're going to find the second derivative using the quotient rule. So using the quotient rule, the second derivative here would equal low, don't do anything to it, d high, which is 2x, minus high, don't do anything to it, x squared, times the derivative of the bottom, which is y prime, all over the denominator squared. Now notice this is the second derivative, but it's not in terms of just x. It has, or I should say not just in terms of x and y, it also has a y prime here. But we know what y prime is. Y prime is x squared over y. So we can do a substitution here by substituting in what y prime is. Y prime is x squared over y. So simplifying my expression, I get my expression for y double prime. Now I did a little bit of algebra there first, which you could do, or you could just substitute that expression right in. So there's our section 3.5 beginning PowerPoint. Make sure you go back and look at all the worksheets that we have here. I'm going to be putting up another video regarding the worksheet where we have implicit